Welcome friends. In our previous number lecture, we have completed up to 85 number question. Okay. So in this video, let's start from 86 number question. This is the 86 number question. Read the question. It is given that if sigma vector is the Pauli spin matrix and r cap is the unity vector joining the distance between the proton and neutron, then the tensor force in case of a deuteron is due to the potential V equal to VTR S12, and in the question we are asked to find the expression of this operator S12. Okay, that is the tensor operator, tensor force operator. Okay, so how can you find? Let's see the solution. You see, whenever you talk about the nuclear potential, it consists of two main components. Okay, and among the two components, there is a major component which is known as the radial dependent part. Okay, that is the central part, central force that comes from the central potential. Okay, and that part is this. This is the central potential part. Okay, this is the, and its contribution is almost 96%. And there is one, that is, this is the central part, and this additional terms, okay, is due to the non-central part. That means this part, this remaining or the residual part of the potential depends both on the radial part and as well as on some spin, like in this part. This is tensor operator. It depends on the spin. It is PLS, that means spin orbit coupling. Okay, and it is SS, that means spin interaction, and that interaction leads to a energy. Okay, that adds to energy or subtract energy. That is different thing, but all those energy, residual energy, comes into this non-central part. But this VCR, you see this part contributes 96% to the nuclear potential. Okay, and this part, logically, this will contribute to 4%. Okay, so among this part, if you see, there is one term, potential term is here, that is VTR S12. Okay, this part is asked in the question. You see about this part, VTR S12, and you are asked to find the expression of this tensor expression. Actually this S12 is the operator. This is the operator. We have to find the expression. You see, it will lead large derivation. So it is better to remember it in a logical way. Okay, so it is the tensor part. Okay, you see, and its expression is 3 sigma 1 dot r vector sigma 2 vector dot r by r square negative sigma 1 dot sigma 2. Okay, and if you want to neglect this r vector, then you can replace it with the r cap. Okay, and this sigma 1 dot sigma cap, this first term, you see this term, it represents the spin orientation dependence part. Okay, that means if you see inside the nucleus, okay, inside the nucleus, whenever there is nucleons are present. Nucleons means what? Proton and neutron. Okay, they are combined and they are called as nucleons. Okay, so when these nucleons are present inside the nucleus, every nucleon, that means it may be proton, it may be neutron, both will act as a dipole. Okay, and their dipole moment is like this. Okay, it may orient in any direction. Okay, and there may be a distance. That distance is known as r cap. This r cap. Okay, and this is the unity vector in that direction. Here it is in this direction. Okay, that means the gap between proton and neutron. And in the nucleus, there is it does not mean that there is only one proton and only one neutron. That is the case of neutron, you know. But ideally, when you talk about large number of nucleons in which there are large number of a number, that means atomic mass number, a equal to, let's suppose, 30, 50, 40, 200 uranium, 235, like this. So in that case, there are large number of orientations between these proton and neutrons. Okay, so if there is a large number of orientation, there may be a angle between them. Like I am taking here only one proton, and I am taking only two nucleon case. Okay, so it is proton. There is one proton, and let's suppose this is one neutron. Okay, so they may orient in some direction, and that orientation makes some angle with the unity vector. Okay, so with that unity vector, that orientation will leads to this energy. Okay, it leads to this energy, and the operator that is operating between these two nucleons, okay, that is the force operator, tensor operator. Okay, force tensor operator. Okay, like this. For analogy, if you are not able to remember it, what you have to do? You have to do a analogy. Like for example, dipole interaction. In electrostatic, you may come across this type of interaction in electrostatic, where there are two dipoles and you want to find the dipole potential energy. Okay, there may be a interaction between the two dipole. Due to that interaction, energy will be created or stored, okay, inside the electrostatic field, and that energy, that potential energy, is this minus 1 by 4 pi epsilon r cube. This term, you see, this term is very much analogous to this. You see, here it is Pauli matrix, here it is only this dipole moment term. Okay, similarly, in case of magnetostatics, like let's suppose there are two loops. Okay, two loops, one is current, one is taking current, carrying current in this direction, let's suppose, and there is another loop which is taking current in carrying current in this direction. Okay, so there may be a magnetic moment, okay, in this direction and in this direction, and due to that direction, that magnetic moment, let's suppose this is m1 and this is m2. Okay, so they will create an interaction between them, and that coupling interaction term, okay, is this energy creates this energy, you see. And here also, this is the same kind of expression that we have that we have faced in this case, you see. So if you are not able to remember this in this way.